CosmoQuest Astro Office Hours stream. I am your host, Dr. Matthew Richardson, and give me a quick second to go ahead and set up here. The local time is now 12:02 p.m. Central. So let me first go ahead and navigate to Twitch. I know there's some black space on the screen right now, and I'm going to resolve that in a minute. But let me go ahead and first make sure that I'm actually streaming live first. Or better yet, well, yeah, let's do that first. That's actually the better thing to do. And then we'll take care of that black space. But today's idea is to work through a problem, but using a computer program to do it. So we need to go over to Twitch. Let's see what we got here. All right, I am live. Let's refresh the page, and I'm going to go ahead and pop out the chat. That way I can be able to communicate with you guys. All right. And there we go. And I'm going to do some slight modification to my setup here. So let's. All right. So what we're going to do, we're going to move this up. All right, that's better. Hey, Uncle Bill Druin. Hey, Peter. All right, that's a lot better. Oh man, I'm sorry to hear that. The Soyuz or is that no Soyuz launch. Hey, Bill Wink. Hey, Guido. All right. So typically, whenever I do these calculations, we do them like by hand, and that works out just fine. But this time, we are going to use a computer program to do it. All right. So I'm actually going to kind of cheat here a little bit, so I don't have to worry about setting up the typical structure that I use for computer programs that I write. I've kind of just copied the information from one of my past streams. I'm just going to modify it. But nevertheless, I'm going to go through how I'm modifying it and why. Hey, Nancy. Well, I'm happy to hear that you can watch it today. Hey, Hexa. All right, let's go ahead and get to it. And let's get rid of some of that black space there. So, the very first thing I'm going to want to do is I'm going to want to modify this one single source code file I have here entitled Artificial Gravity Plot, which was one of the source code files that we created for one of our previous streams. But let's go ahead and modify that, and I'm just going to call it for right now energy and momentum, because that's kind of what the problem focuses on today. Energy momentum. All right. .cc. So that should definitely change the name of the file. Let's go ahead and open it. So Emacs energy and momentum. Let me quickly make some formatting changes to the size of the Emacs text editor window. And let's go ahead and load that up onto the stream. So where are you? Here you go. And there it is. All right, so we're not going to be making any plots today. There's no need to make plots. We're just going to be doing some calculations, though. And we're going to allow the computer to do the calculations for us. But to do the calculations, the computer has to have the appropriate functions to do it. So what I'm going to do is I'm going to first off delete all these header files that have this capital T and then the name of the file, because that's for the plotting packages that I use. So I'm going to get rid of that. This will be our main function. Get rid of all of this. It's not really needed right now. All right. And we can actually define our functions within this particular file, which will make it really easy versus me making up different files for the functions. I'm going to have to check that out, Peter. I didn't get to see it just quite yet. All right. So today's problem actually comes from my physics book. And it's related to the energy and momentum of subatomic particles. But before we get into that, we're going to go ahead and write out the functions for calculating the momentum and the energy of a particle. So we're going to first start off with, let's have one function that for the most part, I'm just going to name it as, so first up, I needed to return a value. So more than likely, let's have it return a double. And we're going to call the function, put a capital C, and put momentum. And we're also going to have, I think I said energy as well. So double, let's put a capital C, energy. And later on, I'll explain the reason why I'm using these capital C's in front of momentum and energy. All right. So for the momentum equation, we're going to, of course, need two variables. We're going to need the mass of the particle. So I'll put that as a double as well. So double mass. And we're going to need the particle's velocity. And for the energy of the particle, that's right, Hexa, you got it, m times v. And so, yeah, when we get ready to write out the actual definition of our function, that's exactly what we're going to end up using. And so for the energy of the particle, in this case, we want to know the kinetic energy of the particle. I want to be more specific about that. The kinetic energy of the particle, we're going to again need the particle's mass and again its velocity. So I'm going to go ahead and scroll through our main equation, start deleting some more stuff because we don't really need all of this stuff. Boom. We can erase that. We can erase all this plot stuff. And I can erase that as well. So now we have, for the most part, a very, we have a main function with absolutely nothing in it so far, but we will get to that in a second. And after the main function, I'm now going to actually define our functions. All right. So for this very first one, and really, I mean, I know I put it up here. I put double mass and double velocity for both of these functions. Whenever you're doing a function declaration, you don't actually have to define what the variable names are. You just have to define their types. But in this case, I mean, it's perfectly okay for me to put their names. I'll leave it like that. So down here, once again, I have the information for the declaration, and now I'll define the functions. And so, as Hexa has already pointed out, for our momentum equation, we're just going to simply return the mass times the velocity. And for our energy equation, we are going to return 1/2, or I'll put 0.5. I mean, it doesn't make a difference. I can put 1/2. But for some good reason, I've always learned it's best to, if you can, to multiply versus dividing for purposes of speed. But I don't really know if it, I mean, in this case, it's not really going to make much of a difference anyway. 0.5 times the mass of the particle times its velocity squared. And I could put velocity times velocity. Yeah, I'll just do that actually. Or I could use one of the functions, the built-in functions, to do the square of a variable, but this works just fine as well. All right, so we've defined our two functions that we want to use for today's problem. Yeah, you're right. I could do it as mass times v divided by 2. I remember a while ago when I was trying to speed up a program that I wrote, there were it was a lot of division in it, and someone one time told me, was like, we should see if we could cut down on the division. Or no, I had a loop, and the loop was doing a lot of division. Why is the v squared for kinetic energy? I will definitely answer. Well, I'll give an answer to that soon. But give me a second though. Let me go ahead and do some more stuff really quickly. All right. So I want to write the. I want to actually write out somewhere what the problem is, so we can keep track of it. Or better yet, I can write it directly into the program. All right, so the very first problem we're going to do, and I'll get back to declaring some variables in a second. Just write it here. The very first problem we'll want to do is we're going to calculate the kinetic energy and momentum of a proton traveling, in this case, we're going to say at, I'm going to make up a value. Let's say that it's traveling at 100, so 10 squared meters per second. Let's start off with this particular problem. And I like to try to make my programs look pretty as well, which is the reason why I'm doing what I'm doing right now. All right, so let's do this very first problem. And so to actually calculate that energy, we're going to need to define a variable within the main function to hold the values of the kinetic energy and the momentum. So within the main function, I'm just reading over your comment there, Hexa. The efficiency of a rocket engine is connected to the average kinetic energy of the particles coming out. That makes sense to me. Okay, because in that situation, the particles that are coming out, it's like they're departing momentum onto the rocket itself. So let's see. I want to be able to find two variables here. Let's just put them as energy, and let's put this one as momentum. Let's go ahead and calculate their values. So for energy, it will be equal to, and I can just copy and paste. Oh wait, before I do this actually, I need to, within the main function, also declare. So here I need to also declare the functions that I'm going to be using. External functions to the main function, that is. So I have this. I'm going to go ahead and get rid of the mass. So even though I could keep it, I'm pretty sure I can keep it. I'm going to go ahead and get rid of the actual like names of the variables that I'm passing to the function. These functions. Let's go ahead and let's redefine the word, or basically declare them within the main function first before using them. Okay, that should be good. And now I can actually use the functions. So for energy, also noting that the mass of a proton, this is C++, Nancy. Yeah, I love to write my programs in C. C++ or C, either one works for me. So the mass of a proton is equal to 1.67 times 10 to the negative 27 power. And this is going to be in units of kilograms. Let's do this. All right, this will be a little bit better. Hey, Adam. And the good thing about actually doing it this way is that if I want to keep making a series of calculations, and I've already defined my functions and everything, it'll be easier to do. All right, so we have all the information we need. So I actually need to produce, or not produce, but create one more variable actually. Mass. All right, so that's good so far. So I know that my mass has to be equal to 1.67 times, I think I can just do this, power. Well, I don't have to do this. Actually, I could just do it like this. I think it understands this. E to the 27th power. It should understand it. All right. That's that. And I know our velocity. So that's one more variable I have to create. within the main function, that is. I know that the velocity is equal to, in this case, 1e2. Noting that the unit, and so whenever you do a program like this, you should always make sure that you keep track of units. Oops, wrong way. Unit is going to be in units of kilograms for the mass of the proton. And for the velocity, which in this case we're not really worried about the direction. So really, the speed of the proton is going to be 100 in units of meters per second. All right. So to calculate the energy of the proton in this case, it's kinetic energy. I might actually want to make a distinction there. So I'm going to change this function to be kinetic energy, actually. So I'll change its corresponding definition. That's good. Here I'll just put a K for kinetic energy. And here also, I think I put kinetic. All right. So I think everything should be good now. And I can go ahead and I can plug in the values for the mass and velocity. So mass is going to be here. And velocity is going to be the second argument I pass to the C kinetic energy function. All right, I believe that so far so good. And the very next thing I want to be able to do is define what the momentum of the proton is given the conditions of this problem. So its momentum would have to be C momentum. And again, I could just simply pass the exact same arguments. And of course, we're going to want to see what our final answer is going to be. So we're going to output to the screen the kinetic energy is going to be K energy new line, and then we're going to put on the next line underneath that the momentum of the proton Wait, you said so luck comes 3 times? What is that? Or in threes? Hey, multi. Hey, multi. I don't want to mess with the name there. But yeah, today I'm just gonna do some very simple problems, in physics. So momentum of the proton is basically just going to be whatever we end up getting from the momentum function. So momentum. Let's make sure everything's good there. I want to make sure we're keeping track of the units too, so I'll put kg for kilograms. And here momentum is going to be in units of, what am I doing? That's incorrect. I'm sorry about that. That's incorrect actually. So this is in SI. So the energy is actually going to be joules. So J for joules, and the momentum is going to be in units of kilograms times meters per second. Let's just do that. I think that's good, and I can end the line here. And I think that that's it for the most part for this problem. And of course, there's going to be a lot more to it, but this is how I think we should be able to set everything up for being able to generate the solutions for this problem. So now we need to go ahead. So now we need to go ahead and make sure everything else with the program is set up appropriately. So I've defined the main function in the functions it needs to use. So going back to my terminal here, and I have 3 tabs open. One tab is going to be dedicated towards the source code directory, which I'm currently in right now. The middle tab is going to be dedicated to the directory that includes my makefile. And so let's go ahead and open that up as well. And again, guys, I'm basically just taking stuff that I've written before and I'm modifying it. So my executable 1, let's make this bigger actually. All right. So the variable entitled executable 1, we need to modify what the name of the executable will be. And in this case, I want it to be the same as what I've entitled the file name, the source code file name to be. So energy momentum. So I go here and I'll put that as that. And so in the object directory, I'm going to create an object file also called energy momentum. And as far as the rest of the make file is concerned, everything else is it's pretty automated, so it's going to be just fine. I wrote this make file a long time ago, and I always reuse it because it's really easy to modify. Alright, so far so good. My make file has been modified. I've saved it. My source code file with my main function is done. So now I need to go to the bin directory, which is going to be my first tab in my terminal. And I can remove the executable that's already in here. Alright. So now I'm going to go back to the directory with the make file, and I'm going to go ahead and run the make command, which will compile the function. Let's see if I get any errors. Hopefully I don't. Alright, it's compiled. So we should now be able to go to the bin directory, which is where all my executables are going to be stored. Run ls, and there it is, entitled energy momentum. And because my main function doesn't require any arguments, I should just be able to run the program directly. And it will give an output. So let's see what we get. Alright, so our solutions. That the kinetic energy of the proton, given the conditions that we've passed to the functions, will end up giving us 8.35 times 10 to the 30 joules of energy. And check something out really quick. Yeah, that is completely wrong. And the reason why it's wrong is because my mass of my proton is extremely large. That should be 10 to the negative 27. So let's make that correction. Alright. So, and this is another reason why it's so much easier to work with a computer program, because, and also difficult at times too, because if you make a mistake, I mean, that mistake early on mistake, it propagates to the rest of the problem. So this should be negative 27. That's corrected. We're going to save it. We're going to recompile. It compiled, and now we can rerun it. And there we go. That looks a little bit more acceptable. So we get 8.35 times 10 to the negative 24 joules of energy, kinetic energy that is. And the momentum of the proton is going to be 1.67 times 10 to the negative 25 kilograms times meters per second. Good. That's our first part of the problem. Now here's our second part of the problem. I'm going to keep everything we've done so far. I'm going to go ahead and copy and paste the original problem down below. But I wonder what happens to our problem if the proton is now traveling at a speed of, let's say, 8.4 times 10 to the 7 meters per second. And again, we could rerun the exact same we can rerun the exact same not parameters, but the exact same variables, but with a slight modification to the velocity. So now I'm going to change the velocity. I'll keep everything else the same. So now the velocity becomes 8.4 times 10 to the 7. This time, I'm going to rerun my two functions I've defined. That is C kinetic energy and C momentum. And we're now going to output the new kinetic energy and the new momentum values. But I think I might also want to specify what the initial velocity is. So I'm going to modify my output statements. I'm going to say given a speed of we'll put velocity here. Given the speed of that velocity. All right. I think this is what I want. And this needs to be in meters per second. All right. So I'm going to modify the output statement below as well. And I realize I've just been talking here and I haven't even looked for a moment at the comments to make sure everyone's like following what I'm doing here. All right, so that should be good. I think I can now run I can recompile the algorithm or the source code, and I can run it again now. Let's go ahead and do a clear. Let's rerun it and let's see what we get. Okay, so this is the new kinetic energy and the new momentum of the proton, given that we're at a speed of 8.4 times 10 to the 7 meters per second. But my question now is this new value that we've calculated, is it accurate? And so that's pretty much what I'm asking you guys right now. Is it accurate? What do you guys think? Anyone there? So earlier, Hexa gave me these equations for the kinetic energy and for the momentum, and they're perfectly right. They're perfectly right. But they're only right underneath certain conditions. I'm not too sure if you guys are still there. Let me see something really quick. So let's see. Okay, no, that works. So what do you guys think? Anyone knows why our new solution has kind of is not as accurate as it could be? Okay, all right. So just to catch you up, Uncle Bill Jordan, we've run two different sets of problems, but for the most part, given the same conditions. So we have a proton. In our first scenario, we have a proton that's moving at a speed of 100 meters per second, and we've calculated its kinetic energy and its momentum. And in the second problem, we have a proton as well, but this time it's now traveling at a speed of 8.4 times 10 to the 7 meters per second. We've used the exact same equations, and I'm going to say we've used the classical equations for calculating the energy momentum. And that's the equations that Hexa gave me earlier, where the momentum is equal to the mass of the particle times its velocity, and the kinetic energy of the particle is equal to the mass is equal to 1/2 times the mass of the particle times its velocity squared. Oh, you can't hear me? I could. So yeah, Tom Van Scotter. So you're right. I could pass the mass and the velocity as as command line arguments. In this situation, I've just hard coded them. But it wouldn't be a really hard modification though. In fact, let's quickly do it. That way we can well, no, there's a reason why I'm doing it this way actually. Nope. You know what? We're gonna go with Tom Van Scotter's recommendation. We're going to go ahead and pass not the mass, but just the velocity of the particle. We're going to assume the particle is going to always be a proton. So to make this modification, I can go here for the main function and its arguments. I think it's something like arc C. I'm going to say something along the lines of int arc C. Let's see, and I think this is going to be char star. I could put this as a. So I typically do this. And now what I want to do, double velocity. So what I'm doing here is I'm going to go ahead and use Tom Van Scotter's suggestion, and I'm going to modify my main function such that I can pass arguments to it. And the main argument that I want to be able to pass is the velocity. So given this, I can keep that. So I'm going to modify it such that I can now get rid of this, actually. I don't need this. And the reason why I'm doing this is because we'll be able to pass any velocity to the main function. Of course, assuming the particle is going to be a proton. So my velocity is going to now be equal to arg v, I think this is going to be 1. And I think that makes the appropriate changes. So traveling at user-defined velocity. All right, that should work. So I've made a few modifications to the program so that we can pass any velocity in units of meters per second to the equation. So it appears that I may have cut out for a moment there. And Hexley, you said the proton is going about 1 kilometer per second faster than orbital velocity. All right, so I'm gonna rerun the algorithm, or I'm going to recompile the algorithm, make sure that my changes are okay. Oh, right. I have to convert that. What's the command for converting from a string to from a char variable to a, let's see. I think I can use, not string, because it's, is it I to A? Not I to A, but A, let's see if this works. A to F, I believe. I think I can use this. Unused, okay, so let's do this. So I can actually use argc in my, even though I don't have to worry about it. Let's do this. Verify parameters. So to avoid getting any more warnings from compiling, I'm going to go ahead and put this condition in. So if argc is less than 2, I'll just have it return -1. All right, that should work. And I'll recompile it. All right. So now I'm going to go ahead and pass and I think it'll understand this actually. Let's see. All right. Perfect. All right. So I was trying to get it earlier that the new answer that we're getting right now is less accurate because we're using the classical form of energy and momentum. So whenever a particle begins to move faster and faster, you have to start worrying about relativistic effects. And so our current definitions for energy and momentum don't work given the speed at which the particle is now traveling at. And so we have to define 2 more functions. So I'm going to go up top and I'm going to now copy and paste our initial definitions. And now I'm going to, instead of having a C, which I put there for classical, I'm going to now have an R. Let's put R for relativistic momentum and relativistic kinetic energy. And again, I'm trying to remember the equations. I believe they take on the exact same parameters. They worry about the mass and the velocity. But I need to define one more function though. And that function is the Lorentz factor, gamma. So double, and I'm going to put this as gamma. And it only requires that you pass the velocity to it, which is one variable which will be a type double. So I'm going to go ahead and copy and paste these new functions that I've declared here. And I'm going to now define them after the main function. And really what I want to be able to do is make a comparison between how far off our classical answer is to our relativistic one. And I'm seeing I have 12 minutes to get this done in. So let's see. Relativistic momentum will actually require 3 variables to be passed to it. So I'll need to modify that up top, but let's go ahead and define it. So I need to return, and the 3 variables that it needs are gamma, it needs the mass, and it needs the velocity. All right. And so it's going to basically just return the product of these 3 variables. So gamma times mass times velocity. And then the kinetic energy, sorry, again, it's going to also need gamma. I'm trying to remember the equations in my mind. If I get this wrong, guys, just go online and type in relativistic momentum or relativistic kinetic energy to make sure I'm doing this right. So, and I think also, no, I think it just needs those 2 things. Everything else will be a constant. So it just needs gamma times the mass for the type of equation I'm gonna write out here. So in its case, the relativistic kinetic energy is basically going to be the total energy of the particle minus its rest mass energy. And we can write that out as gamma minus 1 times the mass of the particle times the speed of light squared. So speed of light times speed of light. And I'm going to define what the speed of light is inside of the function. It's not the best way to do it, but it'll work. And this has to also be in units, in SI units. Excuse me. So 3.0 E8. I think this is right. Let me quickly make sure I put what the unit is. Unit is meter per second. Okay, I think so far so good. And note that the mass that I'm using is the rest mass. And lastly, the Lorentz factor, or gamma. We will be returning, I believe it's 1 divided by the square root of 1 minus, and I'm going to put beta squared. So beta times beta. But we should note that beta is basically just the ratio of the actual velocity of the particle divided by the speed of light. So again, I'm going to have the speed of light, and I'm going to have beta, where beta is equal to, so I need to pass the velocity to this function. It's equal to the velocity divided by the speed of light. And beta is unitless because it's velocity divided by velocity. And so I think that's good. I need to go up top and redefine what our kinetic should be, or our momentum. Should have 3 doubles passed to it. All right. I think that's good. Let me look at the comments really quick to make sure that I haven't missed anything here. So, hey, Closloth. All right, let's see what you got here. You can cast float, but I think it loses. Yeah, you're right. I can cast it in terms of a float. And by doing it in terms of a float, if the function was like really heavy with math, floats would be better if I didn't really care about precision, because it'll help the program run faster. Oh, are you talking about the value that I pass to the main function? I can cast it as a float. I think that's what I might be doing that actually. Oh, thanks. I'm just quickly going through the comments here. Yeah. Typically, what I would do is I would write up a completely different class and define some functions there, but to make sure that this goes faster and I can get to the answers in time before the hour is up, I'm doing it this way. All right. So I think so far so good. I think everything's defined properly. 6 minutes. All right, let's get it done. So what I'm now going to do is I can keep all of that. We're going to run 2 more equations, or we're going to run our new set of equations. So let's define a new variable, gamma. Okay. So gamma will go here, and all right, and we got to pass it the velocity value. So that will give us the gamma. And for the kinetic energies now, we're going to be using the relativistic forms. And so for kinetic energy, I only need to pass gamma, and I believe it was wait, did I make a mistake here? Right, it was just gamma in the mass. However, for the momentum equation, I need to pass gamma, the mass, and the velocity. And really, I could just pass really, I could just pass the relativistic form of the momentum equation, the mass and velocity, and have it calculate the gamma factor or the Lorentz factor within the function. But I think this is a good way of doing it. Yeah, you're right. A to F is a float, even though I've defined the variable to be a double. But I don't think they actually have a function that does Oh, they might actually have a built-in function that actually gives a double from like a string type variable. All right, so I think this is good. I think this works. So I'm going to go ahead and do the exact same statement. So given a velocity of blop meters per second, relativistic values are and I think that this should be good. Kinetic energy of the proton and momentum have been redefined. All right, I'm going to save this. I'm going to go ahead and I'm going to recompile. And hopefully I don't run into any errors. Good so far. And we're now going to rerun the exact same command that I did before for the executable. But we're now going to be able to see what the value, how the value changes for the classical case versus the relativistic case. And so, given the same speed, you can see that the kinetic energy here is larger than the kinetic energy you get from the relativistic case. Still same order of magnitude. It's just that it is larger by a factor. And the same goes for the momentum. So it appears to be the classical equations end up giving you higher values than the relativistic equations. And you could calculate. I'm running out of time here, and I would do this, but you can calculate how much of a change that is, right? The equation you'd use is you can use something like along the lines of the classical value minus the relativistic value divided by the relativistic value, and that should give you the error. But I'm out of time here, so I'm not going to do it. But it goes to show that it's very important that whenever you are doing a problem, you have to make sure that the physics that you're using is relevant. So that's today's problem, guys. I remember when I first started off doing physics, if someone were to ask me, when I first started, that is, if someone were to ask me, hey, how do you calculate, for example, the kinetic energy and the momentum of a particle? I would, without any doubt, I would have went to the classical equations because that's what I knew. But after a few semesters of physics, you learn like, oh, this doesn't always apply. But the fun thing about the relativistic equations I believe, are that they, in certain limits, they do reduce to the classical cases. So, but yeah, I figured this would be a really fun time to do a kind of like a computing / physics type of problem. So I'm reading through the comments now. Oh, that is it, right? I could use. So yeah, it's 6 p.m. now, guys. I'm sorry to hear that. Are you talking about what I'm talking about here, Peter? It's a bit over your. It's not over your pay grade. Steak sounds really good right now. I'm actually in the process of trying to lose some weight, so I haven't seen a steak or smelt one in a while now. But just by you saying that, it's kind of making my mind go towards me going out and getting a steak right now, from anywhere, because it is lunchtime right now for me. But oh, rub it in, why don't you? Watching while you eat lunch. Yeah, one of these days I'm going to stop by your stream and hopefully it's around lunch or dinner time and I'm going to say the same thing. Slingshot around a big enough gravity well. You enter a time warp. That's funny. But yeah, guys, thanks for stopping by. I'm gonna see if I can start to. And again, today's problem was kind of like, I picked it right before our stream, and I figured I'd try to make it a little bit more interesting by adding, a little bit of programming into it as well. All right, guys. Thanks for stopping by. I hope you guys enjoy the rest of your afternoon. I will try to start getting some ideas ready for my next stream. If you guys have any, by all means, just reach out to me through the Weekly Space Hangout Crew Slack if you have access to it. And all right, guys. Thanks. Bye. Oh, you said go on? All right, guys. Bye.